Okay, so let's start today's class. So in the last class, we introduced the Landau theory for superconductors, where we considered uh, free energy for superconductors S, which is something like F0. This is for normal state. And then we had plus alpha psi square plus beta by 2 psi to the power 4, where alpha and beta are some constant, temperature dependent, constants. Precisely, we consider only alpha to be a temperature dependent constant, and beta is some sort of beta 0, which is a purely constant. Yeah. And her psi is order parameter, which is 0 if temperature is greater than superconducting transition temperature, and non-zero if temperature is lower than superconducting transition temperature. Basically, where we are in the superconducting region, then psi is not equal to 0. And after minimizing f with respect to psi, uh, that means, sorry, del f del psi equal to 0, we got that psi uh, was of the form of mod psi rather root over minus alpha by beta, right? Where we considered alpha to be alpha 0 t minus tc. Alpha 0 is again a constant, and beta is approximately beta 0, no temperature dependence in beta. Okay. So then we had psi equal to root over minus alpha 0 t minus tc by beta, then plus alpha 0 tc minus t by beta, right? So that means that when, sorry, it should be when t is less than tc, then psi is real. This is what is needed, because psi cannot be imaginary, right? And the free energy for superconductors with respect to psi was of this form. So this is free energy for superconductors, and this is psi order parameter. So if we have, this should be symmetrical actually, but so something like, so this is for t greater than tc, where psi equal to 0, right? Only solution is 0. What is happening? Sorry. So the only solution is 0 for t greater than tc. Now, if we have t less than tc, then we had solution of some this form. T less than tc, where psi not equal to 0. We had psi 0, and this is minus psi 0, right? because this was mod psi, remember. Otherwise, we got psi squared to be minus alpha 0 t minus tc by beta. So we had two solution of from this equation. Actually, three solution. Either psi equal to 0 or psi square equal to minus alpha by beta. Psi equal to 0 is for this case, and for this case as well, t less than tc, there is one solution here, 0, but this is not the stable solution, right? So not stable for t less than tc, because uh, the free energy can be lowered if we go to the psi 0 or minus psi 0, right? So this is rather metastable state. Metastable state where there is local minima or local maxima. In this case, this is local maxima. And these are the true minima points, and this gives stable solution. These are the stable solution. Okay. And where psi 0, this value is precisely this part, psi 0. Okay, so what this tells us necessarily is that when we talk the superconductivity, the phenomena of superconducting phase transition in terms of Landau theory, the Landau free energy is only have solution at psi equal to 0 for for temperatures greater than transition temperature. As we lower the temperature below the transition, as we go to the below the transition temperature, then we have some finite solution, finite minimum solution, stable minima for this fs function. Okay, so that means there is finite order parameter. So that this indicates that the system is ordered, system is in a ordered state of superconductivity. So from here, one very insightful information we can get that how how order parameter, I'm writing in short, order parameter psi behaves with temperature. Mhm. So this can be a short MCQ type questions, right? So psi 0 we have seen that alpha 0 t minus tc by beta. So we can write this as alpha 0 by beta and root over t minus tc, right? So if we plot it with temperature, then psi 0 and then temperature. So it will something like this type of plot will be there. Okay? This point is transition temperature. So above this transition temperature, psi is identically 0, psi equal to 0, and in this region psi not equal to 0, and the behavior with this temperature is root over t minus tc, right? So this is generally a part of scaling theory for mean field analysis, where we get to know how the order parameter behaves with temperature, or maybe if we apply magnetic field, then how psi 0 behaves with magnetic field. So maybe 1 by delta or something else. Okay, now whenever we talk about superconductivity, the transition. Okay, just a sec. Okay, so whenever we talk about superconducting transition from the normal state, then we have uh, told, or phenomenologically when we study, we have it has been told that specific heat CV versus temperature, there is a sudden jump in the specific heat, right? So suppose I have a normal state specific heat like this, and this is the transition temperature. Then for superconductivity, it will be something like normal state, and there is a sudden jump and then again drops. So now we will understand how this how how we can understand this specific heat behavior from this Landau theory. Okay. Okay. So what is the formula for specific heat? So there are many ways to do it. So the simplest thing we have in mind is the T del S del T, right? Where S is the entropy. And what is S? How can we get S from the free energy? This is minus del F del T, where F is basically the Fs, Landau free energy. Okay, so now let's evaluate first S and then Cv consequently. So del T of F, that means minus del T uh, F at psi 0. So whatever we will do at the after minimizing this energy function. Okay, so after minimizing this energy function, otherwise this will not make sense. So F at psi 0. So let's evaluate first what is F at psi 0 is. So F at psi 0 will be, we had F s equal to alpha psi 0 square plus beta by 2 psi to the power 4. So this means alpha mod psi was root over minus alpha by beta. So the square will be minus alpha by beta plus beta by 2 alpha square by beta square, right? Just a second. Yeah, fine. So this will be minus alpha square by beta plus alpha square by 2 beta. That means minus alpha square by 2 beta. So this is Fs at psi 0. So minus del T of minus alpha square by 2 beta. That means del T of alpha square by beta. Now we have assumed that beta is constant, beta is beta 0, independent of temperature. And alpha is equivalent to alpha T minus Tc, right? So S will be minus half, sorry, plus half del T beta and alpha 0 T minus Tc. Okay, so this is square, alpha square. Uh, this is square, this is square. So alpha 0 square by 2 beta into 2t minus Tc, right? That means A is equal to minus alpha 0 square by beta Tc minus T. So we'll always write in terms of this form. This is just to emphasize that whenever we are all in the T less than Tc limit, whenever we are talking about Landau free energy, okay, because whenever T greater than Tc, we know that psi equal to 0. So the whole solution Fs psi itself 0. So this will give us nothing, no information about the system. As far as the Landau free energy formulation is concerned. Okay, then we'll evaluate CV. CV was T del S del T. That means minus alpha 0 square beta T del T of Tc minus T minus alpha 0 square beta T into minus 1. So alpha 0 square by beta into T, right? So this is CV. So this is CV for superconducting state. And we need delta C, jump in the specific heat. Right, delta C equal to CV, let's say S minus CV at the normal state. But so from this Landau theory, we will have CV for normal state equal to 0, right? Because it doesn't really represent, this Landau theory doesn't really represent the normal states. So we can definitely say this CVS is equivalent to delta C is equivalent to CVS. So there is another more intuitive way to understand this is that Landau free energy is essentially Fs is equal to Fn plus alpha psi square plus beta by 2 psi to the power 4. We are not really concerned about this constant normal state term. Normal state free energy, right? So had we considered Fn from the scratch, then we will also get some Cv corresponding to normal state from this Fn, because then S will have Sn will have some Fn del T, and then from this Cv for normal state we will have T del Sn del T, right? So some term will be there, but we are not concerned about this constant thing, which is more sort of general. We are only interested in the specific heat corresponding to the superconductor thing. So that means delta C is some way equivalent to alpha square or alpha 0 square by beta into T, which says that let's say this is Tc, Cv below Tc, or the temperature below transition temperature, the CV or the delta C rises, right? Linearly rises with temperature. So this will be something like this, right? So this is what the Landau theory tells. This doesn't tell the story of this thing. Ki, let's say above TC there will be similar feature like this and then this, right? So for normal state this will go up like this, but for superconductivity there will be jump or discontinuity of this amount. So the Landau theory doesn't really tell anything about this part, okay? Because this is T greater than Tc part, and at T greater than Tc, again I'm repeating this thing, is psi equal to 0. That means F is equivalently Fs is 0, or at max Fn if you are considering that normal state free energy term. So this Landau free energy theory tells us that around Tc you have a linear increase in the specific heat. So that's what it tells us, and it qualitatively explains. So that means it qualitatively explains the jump in specific heats. So these are small questions which can be given in the exam, right? Uh, so you may expect few questions will be given directly from the assignment, maybe, but these are small questions that will be given, that may be given in part, instead of let's say saying everything do it from the scratch of Landau theory. It can be asked that write down the Landau free energy and then explain the jump in the specific heat. Okay. Okay, so next we will go to the Landau-Ginzburg theory. So far this was only Landau theory. Now we will go to the Ginzburg-Landau theory or Landau-Ginzburg theory, and construct the London's equations basically. Okay. So any questions so far? Any confusion or any questions?
Good evening, sir.
Yeah, yeah. Good evening.
I have a question in assignment third.
Hmm.
Question number 4. Please clear, sir.
Question number 4. Okay. So present schematic plots of order parameter, flux density, diamagnetic energy, and condensation energy at the normal metal superconductor junction at a function of as a function of distance. Okay. Okay. So this has been actually fully solved in one of the lectures actually, week 3. It was probably lecture 2 or 3. Okay. So basically they are telling that normal metal superconductor junction. So you have a let's say normal metal and superconductor. Okay, so then it is saying that how the order parameter behaves, right? Like let's say I have order parameter like this value, and then as we enter the normal metal, it will start decreasing, right? So so this is one of, this could be the behavior of psi. And then flux density means there essentially means we have applied magnetic field. So how the flux density behaves in the superconductor region and normal state region. And then diamagnetic energy and condensation energy. So all of these things actually has been derived in one of the lectures actually. Okay. And another thing is that I cannot really directly solve these problems because we have been instructed not to solve actually precisely. So that is another sort of restriction ki the TA sessions are not to be meant for the solution of the assignment. But yeah, I mean, we can definitely help and understand, make you understand the questions. That's it. Actually. Okay, because some people will sit in exams and they will evaluate things accordingly. That's one restriction. But as far as I remember, it was in lecture 2 or 3, okay, of the week 3. Fully, it has been solved actually. Okay, so
Okay, sir.
yeah, okay. So, okay, so in the Ginsburg-Landau theory, we have some additional term in the free energy function. Okay, so let's say we have free energy. We in the Ginsburg-Landau theory we express free energy like this, which is integration of ddr. So ddr just explains that let's say we are in d dimension, d spatial dimension. And then we have alpha again mod psi square as it was, beta by 2 mod psi to the power 4 plus gamma gradient of psi star complex conjugate dot gradient of psi. So this is the free energy functional. We call it functional, not function anymore, because function. So this is a kind of function of function. Psi of r, now it depends on r, which I have not explicitly written here, because otherwise gradient will be 0, right? If psi is constant, then gradient r of psi 0 will be 0 identically. So this term will not be there. So that is the difference between Landau theory and Landau Ginsburg or Ginsburg Landau theory. So this part is purely from the Landau theory. So essentially, physically, what is happening here? Physically, it has so in the Landau theory, we are assuming that the size is only can be of the form psi 0 and e to the power I phi, let's say, any phase which is independent of position. Okay. Here we are additionally assuming that the wave function or the order parameter is not really constant in the sample altogether, but it has some small variation. It's a function of r. Okay, so that's the difference. And the first order correction we are bringing in the functional or the theory is this term associated with gamma. Another thing to note that is that this is free energy density. When you integrate with the with in the sample or with respect to position r, then you get the free energy functional, right? So it's a density actually, but we'll often call it free energy It's a sloppy language, but yeah, I mean, this is a density, and accordingly, alpha, beta, gamma, the dimension of these things have been accommodated. Okay, so from this free energy functional, we will actually derive what it, the response, or how the superconducting order parameter behaves, or this type of things in presence of magnetic field actually. So we will add another term. Okay, so we'll add uh, superconductors. So this, so let's say we have applied magnetic field B, which can be written as curl of A, right? Now in the Payal's theory, Payal's Payal's substitution, we call it. I have some momentum, let's say P. Then in presence of magnetic field, it goes as P minus Q by CA, right? C is the velocity of light. I am in the CGS unit, and Q is the charge of the particle, and P is the momentum charge. This is the vector potential representing magnetic field. Okay. So now you want to add magnetic field in this free energy functional. Okay. So how do we add? I will write this and then explain. So this is approximation. All of these are actually approximation, because there can be higher order terms in the psi which we are not necessarily considering. Now, given that we are considering magnetic field, there can be higher order terms corresponding to that as well, but we will consider the lowest order term which is necessary. And let's assume that we are in the 3 dimensions, so dq bar and then energy density. So we can actually show that the free energy functional in presence of magnetic field, which is being represented by uh, vector potential A, will be of this form. So this is a bit lengthier to prove, that's why I'm skipping, but this can be in general proved actually. So, and also we have assumed that gamma is equivalent to 1 by 2m star here, gamma of this thing here. Okay, And so how do we write this part, right? So gradient is sort of, okay, so gamma is not precisely equivalent to this term, but let's say we can write that grad psi was there in the initial functional in presence in absence of magnetic field, and there was grad psi, right? Grad psi star grad psi and gamma. We write it, or we wrote it as some sort of p psi square, where p is, we know, minus I h bar del position operator del x. Let's say if we consider only x direction, then this is the right. So so this is precisely like this was actually like kinetic energy. So if we explain more, then uh, let's say psi in absence of a d cube r alpha psi square plus beta by 2 mod psi to the power 4. So it's exactly like kinetic energy gamma grad psi star, sorry, grad psi, right? Now we can think of this as a kinetic energy. In kinetic energy, what happens? P square by 2m is the kinetic energy, right? 2m or 2m star, whatever. So if we equivalent this to gamma grad psi star grad psi, then what we will get? Gamma, and we can write this 2m star, and then P square will be minus I is grad, minus I is grad, just a second, 1 by 2m star minus I is grad, minus I is grad of psi, right? We can write it because this is P, this is also P in the quantum mechanical notation. So this is equivalent to grad psi. So now we are just comparing this. Since P modifies as this term shown here in presence of magnetic field, so we are also adopting this term here. Okay. So doing all this jugglery, gamma equivalent to 1 by 2m and this factor, some factors with h bar, we can get this expression. Okay. And why this is there? B square is the sort of magnetic energy, or more precisely, we should call it magnetostatic energy stored in the system. Magnetostatic energy. So you'll remember from the electromagnetic course that UE, electrical energy stored, is proportional to the electric field square, and magnetic field, or the energy stored due to magnetic field, was the B square by 2 mu, right? Something like that was there. So this is the same thing in the CGS unit. So we are doing in the CGS unit. Okay. Okay. So if of psi a, we have d cube r alpha psi square plus beta by 2 psi to the power 4 2m star z minus q by c a psi square plus b square by 8 pi, right? Now we will simplify this equation. especially this part should be simplified more. Okay, so dq bar rest alpha psi square plus beta by psi to the power 4 plus 1 by 2m star so let's write more clearly h by I that minus q by ca then h by I grad minus q by ca. Okay, so psi operated and then plus b square by 8 pi, right? pq bar alpha mod psi square plus beta by 2 psi to the power 4 plus 1 by 2m star. So this part and the total part, right? So h by I gradient. Okay, so this is mod square since the complex part is involved. So this will be like complex of this, right? Okay, grad psi star and then this whole part h by I grad minus q by ca psi plus this part and this whole part minus q by ca psi star and then h by I grad minus q by ca psi plus b square by 8 pi, right? Equal to mod alpha psi square plus beta by 2 psi to the power 4 as it is plus 1 by 2m star psi star h by I grad star h by I grad minus q by ca psi plus 1 by 2m star so we are uh, extracting psi from that this psi then minus q by ca star but minus q by ca star is essentially minus q by ca because these are constant q and c and a is also real, right? It just represent that real magnetic field because curl of A equal to B. So we don't need to give any star here because we have already explicitly written psi star here. So then the rest part h by I grad minus q by Ca, and then this will be psi. Okay, and the b square by 8 pi. So alpha psi square plus beta by 2 psi to the power 4. You can write 1 by 2m star psi star so this psi star by 2m and psi star by 2m common, then we'll write this part and this part because we can common on the right side this part and this part to be common, right? So we'll have something and common part will be h by I grad minus q by Ca psi plus b square by 8 pi, and this part will be this h by I grad minus q by C a star, right? Because this was the star and this was star. If we do it or don't do it doesn't matter because this whole part is purely real. So d cube r alpha mod psi square plus beta by 2 mod psi to the power 4 plus 1 by 2 m star psi star h by I grad minus q by Ca square, this two part psi plus b square by 8 pi. So this is one of the form for Ginzburg-Landau theory or Ginzburg-Landau free energy functional. So let's say call it this is equation 1. So whatever we did in the Landau theory, we did the minimization of free energy with respect to the free parameters. So in the Landau theory, in Landau theory, the free parameter was only psi, right? The psi, but in Ginzburg-Landau theory, the free parameters are psi and as well as a, the vector potential. Okay, there are two free parameters. So what did we did with free parameters? We did del f del psi equal to 0 and then find out the solution, right? From that we get the information that how psi behaves with t. It was t minus tc to the power half, and then cv was simply proportional to t around tc, right? And many other information can be extracted out. So same thing we will do, but we will have to do two things. Del f del psi equal to 0, that will give us one equation. Okay, so let me distinguish it. So delta f of psi a delta psi equal to 0, that will give me one equation, and then delta f of psi a. So whenever we write this in this way, f of psi a, this means that we are in the Gainsbourg-Landau theory. Delta a equal to 0. This will be two equation. This will give us two equation. Okay, now we will derive this. Okay, so first let's minimize with respect to psi. Okay, so minimize with respect to psi star, let's say. The same thing will happen with psi as well, nothing different. So if we minimize, or if we take derivative of this term, then what will happen? So this will be similar thing as we have seen in the Landau theory. So let's write that alpha psi uh, alpha psi plus beta psi square psi. I'll explain why, how this comes, and then 1 by 2m so equal to 0, right? So how this comes? So whenever we taking, let's say, del psi, right, or delta psi, same thing basically in the limiting case, del psi of alpha psi square. So what is happening? So del psi alpha psi star psi, right? So then it will be alpha psi star. So we have taken derivative with respect to psi star, so we have alpha psi, right? So that's what is there. Similarly, beta psi to the power 4, we can write beta psi square psi star, right? So whenever we take derivative with psi star, then it will be beta psi square psi. And when we take derivative of this term, so this psi star will go away, and the rest of the terms will be there. So that's how we got it. And b is independent of psi anyway. So del b square del psi equal to 0, right? Okay, so then from the first equation we got 1 by 2m star h by I gradient minus q by c a, sorry, square psi plus alpha psi plus beta mod psi square psi equal to 0. So that is our first equation, equation 2. Now we have to take or minimize with respect to a. Second task is a. Now this is a tricky thing because this is a functional form, we have uh, we have some complicated form like this, and then b square, how do I write? B square equal to curl A square, right? Because B is curl A. So we cannot directly evaluate like this in the case of psi. So this is a bit tricky. So let's see how can we do it. So whenever we are minimizing things, we are essentially assuming that there is some value of A and there is some delta A part, right, which is variational, let's say, which varies, okay, around the equilibrium part. So so that's what we will do. We will express A equal to some A0, which is, you can think of like mean value, and plus some variation around that value, mean value or equilibrium value, which is more suitable, which is, let's say, A. Okay, and all of this depends on position, right? Because A is a function of R. That's why depending, matlab, uh, when it acted by Carl, it gives B, right? So basically, A of R equal to A0 of R plus A of R. Okay. Okay. So basically, we need to replace this. Okay. So replace this equation in equation uh, equation one. This equation, and then write down the equation in the to the first order in A, right? So you will get lot of terms because you have curl of A square from the B square, right? And then H by I grad minus Q by CA. This is also square. S- So whenever you put A plus A, then you will get lot of terms. So after doing a bit straightforward but lengthy calculation, what we will get is that f of psi a0 plus a. By the way, so a is small, right? And a0 is the equilibrium value. So we are considering some equilibrium value we have, and around that we have some small fluctuation. Okay. So the more easier way to understand this is, let's say, where we draw the free energy functional. Let's say this point, this part. So let's say effectively we are considering like psi equal to psi 0 plus delta psi. Okay. So I'm talking in terms of psi, but I'm doing in the Ginsburg lambda theory, it is A part, right? A0 plus delta A, or which I am representing as simply A. So A0 is the equilibrium value. So is the psi 0. So I have some psi 0 here, and around this point, let's say these points, I am getting psi, right? And this psi is represented by psi 0 plus delta psi. So that deviation is delta psi, which is very small because we are essentially in the equilibrium limit. So this technique doesn't work. Let's say if I are working here, which is huge difference from this point, right? So that's the essential point. So that A is 0 or the deviation is 0. So then what you will get is that free energy functional psi and A0 plus you will have a term, small a term, a cube r minus q by c a0 psi and multiplied by minus q by c a psi. So all these are basically vectors. Plus 1 by 2m star minus q by c is psi star multiplied by h by I gradient minus q by c a0 psi plus 1 by 4 pi curl of a0 multiplied by curl of a0. Okay. Plus there will be some term which will be order of a square, which we can neglect because a is small. So these terms will be small for a0 much greater than small a. Okay. So this can be rewritten as this calculation have to be done in a bit careful way. This is purely straightforward, but lot of terms are there. So okay, so plus d cube r, then minus q by m star c. So here I missed 1 by 2m star q by minus 2m star c. Then we'll have h bar by I gradient of psi star psi. So we're essentially dealing with this term plus psi star h by I grad of psi dot a. Okay. Okay, so what we have done is simply simplification of these two terms. Okay, some terms will get cancelled and will be left with this term and few more terms, which is plus q square by m star square c square mod psi square a0 dot a from the last of these terms basically. So this and this and this. Okay. we'll have plus 1 by 4 pi curl of b0, sorry, curl of a0 dot a. So this is the total term. Okay. Okay, so someone message. Okay, so now our argument is, so as we minimize the energy, so for minimization of free energy, functional f of psi and a, the coefficient of a should be 0. Okay, so so how do you understand this? Again, let's go back to this Landau free energy diagram. So again, so we're back in this. We'll understand in the terms of psi, because this is the plot here, right? The free energy of superconductor versus psi plot is there. So let's say I have psi, f of psi plus some coefficient, let's say c, some constant delta psi around uh, this equilibrium point, this point. Okay, now when I will precisely get f of psi 0, psi 0, right, f of psi 0, now f of psi 0 is the minimum energy, right? This is the bottom equilibrium point. So there are two options basically. Delta psi itself is 0 or c equal to 0. But delta psi is 0 means we'll get nothing. I mean, if delta psi is 0, then whole thing is 0. We'll get no interesting thing, right? Rather, we are getting, so when we put c equal to 0, that means some coefficient was there associated with delta psi, which makes this whole term to be 0, so that f of psi 0 remains, which brings me back to this equilibrium energy, right? So this equilibrium point, and this c equal to 0 will give me some information about the system, or there will be some equation or the expression associated with it, which will give me some information. That's why we are doing c equal to 0. Okay, so this is in terms of psi 0, but we are doing it in the a, in the free energy or Ginsburg-Landau theory. Okay, so that's the rationale behind putting the coefficient of a to be 0. Okay, so what was our coefficient of a? So all of these are essentially coefficient of a, this part, the whole part basically, right? Because here is linear in a, linear in a, and linear in a. So if we equate this, then we'll have minus I q h bar by 2m star c grad psi star, or so grad psi star psi minus psi star grad psi plus q square by m star c square mod psi square a plus 1 by 4 pi curl of p. Okay, equal to 0. Okay, so this is our final equation from the second constant, minimizing the energy with respect to the vector potential, right? Now this expression is sort of well known in quantum mechanics, right? This is the expression for current density, or at least it is proportional to the current density, because there it doesn't have to be q, the charge may not be there, not necessarily, it depends necessarily on the uh, which current density we are talking about, right? So this is 0, meaning we have, okay, so we will use another expression which is curl of b, basically Maxwell's equation, Maxwell's fourth equation, which is curl of b equal to, in the CGS unit we can express it as 4 pi by c, may have seen here in this term, right? Plus there is some del E del T term, which E is the electric field, which is 0 here. Okay, we are not considering any displacement field, no displacement field. Okay, so this is known from the Maxwell's equation, so we'll put this in this equation. So uh, so basically curl of B equal to 4 pi by c into j. So if we put this here, then that will be 4 pi by c 1 by 4 pi j, right? J is the current density. So then we'll have current density to be mm, so plus I q h bar by 2m star, c will be out, then psi grad psi star minus psi star grad psi minus q square by, sorry, m star c mod psi square a. So this is the current density equation in terms in presence of magnetic field. Okay, so this is equation number, let's say, 3. So first equation we got this, and the second equation we have is this equation, so which is exactly the expression of current density. So this is the probabilistic current density we know from the quantum mechanics. From quantum mechanics, it is probabilistic current, so probabilistic current density. And this is the extra part due to the electromagnetic field. Here only magnetic field. Magnetic field. Okay. Okay. So this equation 2 and 3, equation 2 and 3 are called Ginsburg Ginsburg-Landau theory for superconductors. Okay. So basically, first equation gives from the minimization of free energy with respect to the order parameter psi, and second equation gives the minimization of energy with respect to the vector potential A. Okay. So now let's see how it can produce London equation and the corresponding uh, consequences that we can get from the Landau-Ginzburg equation, right? So if you remember, London equation, when we derived purely from the electromagnetic theory, then we have not considered anything that psi 0, and then there is some delta psi which we can actually call psi r as a function of r. All these things are not considered, right? And London equation has been derived in the context of purely homogeneous system, meaning that psi is essentially psi 0, meaning there is no spatial dependence of the order parameter. So if we take psi of r, so in Landau-Ginzburg theory, psi is essentially as a function of position. So if we take psi of r is equivalent to psi 0, independent of position, then from this equation, equation 3, we will have J equal to minus q square mod psi square and m star c, right, and a, because whenever psi is independent of r, then grad psi equal to 0. So the first term of this equation, so this whole term is becoming 0 for psi equal to psi 0, right? So this was the actually the equation of London, right? Or more explicitly, we can write this as to be uh, minus, sorry, e square ns by m star c, or let me derive it. So for superconductor, q is essentially minus 2e, m star is essentially 2me. M is the electronic mass, and psi square is equivalent to ns, basically Cooper pair density, right? So then q square by mod psi square by m star will be 4 e square ns by 2 me. That means 2 e square ns by me, right? So this way we can simplify. Or we can sometimes actually we represent ns to be the 2 mod psi square, okay, following the other these things. Cooper pair density necessarily involves 2 electrons, so if we take that into account, then just a second, am I doing some mistake? Okay, we can actually keep it like that, as long as we're not confusing it. Basically ns is the mod psi square. Okay, that's perfectly fine. So with this we'll have j equal to minus sorry, 2 e square ns by me c and a, right? So this way we can from the Landau-Ginzburg theory we can actually arrive at the London equation. So this can be one question key, derive London's equation from the Landau-Ginzburg theory. London's equation. Okay. Okay. So this was the discussion on Landau-Ginzburg theory, and then let's discuss something else. So what is really happening is that I'm going through that the assignments, and it turns out that the all the assignment questions are directly from the class materials, right? So I am also going through the lectures. There are only 2-3 lectures per week, so it is also easier for me. And it turns out that the all those solutions are really there in the class lectures. So if you are not able to solve those questions, then I think it is better to again repeat that lectures, because that was nicely presented in a I mean in a 4-week course. That is a very nice presentation, crisp, in a crisp manner. So that's why I am also not solving any questions as well. Okay. Okay, so Okay, so from this equation, from this London's equation, we can have a very nice understanding about the temperature dependence of the penetration depth, which we essentially calculate from the uh, basically London's equation. So let's do that. So we'll go ahead with this equation, okay, not this derivative equation. So we have j equal to uh, minus q square mod psi square m star c m star c a, right? So then we'll have minus 4e square q equal to 2e, and then let's say psi 0 will use that information from the Landau theory. So Landau theory psi 0 equal to, what was that, minus alpha by beta root of this, right? So psi 0 equal to sorry, psi 0 square equal to minus alpha by beta. So then we'll have, so this we can write it as mod of alpha by beta. How? Because alpha was there, alpha 0 t minus tc, right? And we are always in the t less than tc regime whenever we are talking about all this Landau theory, Landau Ginzburg theory. So this can be rewritten as alpha 0 tc minus t, so that this effectively is greater than 0. Okay, so that's how we can write this. So mod alpha by beta and m star c and a, right? So if we take curl of this equation, or before that, let me make it to be j equal to minus 1 by lambda Ginzburg Landau a, this, right? So square, so that lambda Ginzburg Landau square is m star c beta by 4e square. Let's keep it q square. Q square and then alpha, mod alpha. Okay. So this is the equation. Now if you take curl on both sides, take curl on both sides of this equation, then we'll have curl of j equal to minus 1 by lambda gl square curl of a, right? This means curl of, again, what was j equal to curl of b, right? So in SI you have curl of b equal to mu naught j, but in CGS you have 4 pi by c curl of p, right? So if you take this, that means that will be c by 4 pi curl of b sorry, there is extra curl. So C by 4 pi curl of curl B, and then minus lambda GL square. This is simply B, right? Now curl of curl is minus Laplacian of B plus gradient of divergence of B, right? This is just vector formula. C by 4 pi equal to minus 1 by lambda GL square B. This term is 0. Why? Because magnetic monopole doesn't exist. Divergence of B is always 0. So this will be Laplacian of B okay equal to 1 by lambda GL square 4 pi by C B. We can also take it to be 1 by lambda GL square. Okay, this is just effectively doing things, not putting 4 pi and C all and outside. Okay, so we are essentially interested how lambda GL behaves with T. There is a beautiful understanding of this. So let's say lambda GL square is lambda GL square will be this term, right? So m star C beta, let's say, and then Q square alpha, which we can write lambda GL is proportional to 1 by mod alpha, and then lambda GL is proportional to 1 by Tc minus T to the power half. Okay, so this is the how the Landau-Ginzburg length or the London's penetration length varies as a function of temperature. Okay, so there can be simply they can simply tell that how this behaves, derive this equation. Okay, or maybe just a plot, right? So in both of the cases you can derive that from starting from the Ginzburg-Landau theory. I do not know this will come or not, but these are sort of typical easy questions. Okay, but not a very direct questions. Okay, so let's say here we have Tc, and the lambda varies as like this. Okay, because at t equal to Tc, lambda lambda GL diverges, tends to infinity. So this is what it is, and t equal to 0 will have some finite thing, right? Because at t equal to t, so alpha will be alpha 0 t, right? Because alpha equal to alpha 0 Tc minus T, so alpha at t equal to 0 will be alpha 0 Tc. So it will have some finite non-zero value. So this is 0, some finite value. So lambda 0, let's say. So this is how we will behave. Okay. Okay. So next we will have Okay, so next we will derive how, let's say we have a normal state and superconducting junction, or then how the wave function behaves. Okay, that will directly actually help in solving the question 4, but it is not precisely, I'll not precisely solve that. Okay, so let's focus on the first equation that we got from the Landau-Gunberg, which was this equation. So this was our first equation, right? So if we take it directly, first Ginzburg-Landau equation. Okay, and what is the geometry that we have? Let's say in this way, vacuum. Vacuum means normal state. Okay, nothing else. And this is superconductor. Okay, so this is at x equal to 0, let's say. So this is x greater than 0, and this side is x less than 0. Okay? And we assume that there is no external magnetic field that has been applied. So no magnetic field. That is b equal to 0 and a equal to 0. So this will give us 1 by 2m star h by I square, sorry, grad psi, grad square psi rather, plus alpha psi plus beta psi mod psi square psi equal to 0. So we are interested how psi behaves in this case. So superconducting case it was like this. So in vacuum how will this behave, right? So it will directly drop to 0, or it will have some finite decay length, etc. We'll quantitatively find that. And we are also considering, so let's be very clear, consider only superconductor, meaning grad is only equivalent to del x. Okay, del y, del component is not there. That is just to simplify our life. So then 1 by 2m star, we can write this as uh, okay, so h bar square by 4me square, we have used m star equal to 2me. Okay, and then d2 in one dimension, sorry, d2 psi, d2 psi dx2 plus alpha psi beta psi square psi, right, equal to 0. We are also assuming that psi equal to psi 0 f. Okay, f of x, let's say. So where psi 0 is constant, it doesn't depend on the spatial dimension, but fx contains all spatial dependence. Okay. Okay, so then we can write it. Just a second. Give me a second. Okay, so if we explicitly replace this in this equation, then we'll have minus h bar square. Okay, so I forgot a minus sign, right? Which will come from the iota square. H bar square by 4m alpha. So this is just simple algebra. We'll just replace psi 0 fx and then rearrange things. Plus, or rather, let me go to another extra step. Alpha f plus beta f cube mod psi 0 square equal to 0. So then we'll have minus h bar square by 4m alpha d2f dx2 plus f 1 minus f square equal to 0. Right? So what we have used here is that psi 0 equal to minus alpha by beta. So this is a very important result which we will use all along whenever we are discussing lambda theory or any Landau-Ginzburg theory. And then so we'll define something like xi square. So define xi square equal to minus h bar square by 4m alpha, this term, which is actually positive because h bar square by 4m alpha 0 tc minus t to the power minus 1, right? Because alpha, again, alpha 0 equal to t minus tc. So alpha 0 tc minus t. For t less than tc, alpha is positive. Okay, so if we replace this in this equation, then we will have d2f d x2 xi square plus f1 minus f square 0. Right, now we will define another quantity eta equal to x by xi. Xi has a dimension of length, so whenever we are replacing this eta equal to xi by x by xi, we are essentially doing non-dimensionalizing the equation. So we will do non-dimensionalize the equation, right? Because d eta equal to dx by d xi. So this way we can write this equation to be similarly d2 eta equal to d2x or dx to whatever we want. Sorry, this is simply xi. If we replace this here, then we will have d2f d eta 2 plus f1 minus f square equal to 0. This we can again write it as half d Okay, let me go to extra steps. So multiply by df d eta and then d2f d eta 2, and then there will be plus df d, d eta f minus df d eta f cube, right? 0. So which will be, now we can express this equation as, so what we'll essentially do now is that we'll integrate with respect to df, right? So we can actually write this expression as half d df, sorry, df deta square plus f square by 2 minus f to the power 4 by 4 equal to constant. So these two terms we can understand, right? F square by 2 is coming essentially from the integration of df and f, right? And then df f cube is giving me f to the power 4. Now let's understand the rest of the term, this term especially. So what we have essentially done is that df d eta into d2f d eta 2 and integrate with respect to eta. What will we get? This is first term, and then second term will also be df d eta. Then if we integrate double derivative of this term and then integration of this term, right? And then d eta. Let's say integration is I, right? So this is precisely I, right? So that means 2I equal to df d eta square. So it gives me df d eta d2f d eta 2 integration with respect to eta is half of df d eta square, right? So this is the proof. We have used integrate. So here we have essentially done in this line integrate with respect to eta. Okay. Okay. Okay, now to solve this equation we need two boundary conditions. So boundary conditions. So first boundary condition is eta equal to 0 at x equal to 0. Or we can have df d eta tends to 0 as eta tends to infinity, right? So let's understand what this boundary condition actually means. Whenever we are saying eta equal to 0 at x equal to 0, this means that x by xi equal to 0 because eta is that, right, at x equal to 0. So if we think about this equation, then what will essentially we are telling is that let me uh, so at x equal to 0, eta is 0, sorry, f is 0. That means in the superconducting region I had some superconducting order parameter, and then it suddenly drops at x equal to 0, precisely drops at x equal to 0. Okay, so that means there is no variation of superconducting order parameter psi, no variation in the within the superconducting region, right? Because uh, it suddenly drops the moment I am coming to the vacuum region, it is 0, and in the superconducting region it is definitely finite and no variation. So this condition means no variation, means a spatial variation, variation of psi or f, because f contains the spatial variation of psi in superconducting state, right? Now let's understand what this boundary condition means. It says that df d eta 0 as eta goes to infinity. Again, remember eta is x by xi. So eta goes to infinity means goes to infinity. And df d eta goes to 0 essentially means df dx goes to 0. So this thing means that within or so okay, within superconductor, well within superconductor, no spatial variation of superconducting order parameter psi, right? That means the second boundary condition means that whenever I am very so well within the superconductor, then there is no variation, it is like constant, right? But it doesn't talk about uh, the boundary. So it can happen that size uh, constant, no spatial dependence, there is no variation with respect x, but then as we approach boundary there is some variation, and it basically gradually drops to 0, not a sudden drop, right? Like the first a. Okay, so it turns out that the second solution is more feasible, that in superconductor, well within the superconductor we have some constant, and then it drops gradually, okay, as we get out of the superconductor and within the vacuum region. Okay, okay, so this equation cannot be solved exactly. Okay, so that's why we are taking different asymptotic limit. Okay, okay, so if we use this boundary condition, that df d eta equal to 0 at eta tending to infinity, hmm, then we'll have constant. Just a second. Okay, right, fine. Okay, so df, so this condition also implies that f tends to 1 as 1 approaches tending to infinity, right? Or eta tending to infinity, same thing, because that's what we discussed, ki this is sc, this is vacuum, then if when f equals to 1, That means psi equal to psi 0 f is completely psi 0. Psi 0 is independent of x, so that means this is a constant well within this superconducting region. So this is another condition that we can use, okay, to find this constant of this equation, okay. So and this constant turns out to be, if we use that, I am not deriving, this is a straightforward case, constant turns out to be half. So we are left with the equation d2f d eta 2 equal to half 1 minus f square square. You can just do little bit of algebra and arrive at this. And the solution of this above equation is of the form of f of eta tan hyperbolic eta by root 2, okay. So again plug that eta expression, x was x by xi, so f of x by xi equal to tan hyperbolic x by root 2 xi, right? So then the order parameter is psi equal to psi 0 spatial independent part, and then tan hyperbolic x by root 2 xi, right? So this is the variation of superconducting order parameter in a junction of vacuum and then superconductors SC, okay, where x equal to 0, positive and negative, right? So this is how varies. So let's say, so I have some superconductor and it actually gradually decreases like this. This, okay. So this is psi 0. Again, whatever we have told physically, that if you're well within the superconductor, then it reaches psi 0. This is because tan hyperbolic of x goes to 1 when x goes to infinity. Simple algebra, right? So that, and it gradually decreases and it becomes 0 at x equal to 0, where the vacuum starts, right? And this length scale where the gradual decrease happens, this happens over the length scale of xi, this xi, which is basically Ginzburg-Landau. We are not writing GL just to abbreviate things, but this is the typical length scale in which the superconducting order parameter decreases in a vacuum or normal and superconducting junction, okay. Okay, so I hope it was clear, and this is a very important result, okay. Okay, so let's end today's meeting. Thank you for joining and being there. So I'm ending the meeting. Okay, thank you.